Welcome students, and this is Ravi Shankar. So today we are going to study about the electrostatic potential energy of a dipole in an uniform electrical field. See, you know what do you mean by this dipole, and also you know what is meant by uniform electrical field. In our previous classes, we have studied about the potential energy due to charges and due to system of charges. Similarly, we are going to study about electrostatic potential energy of a dipole when the dipole is placed inside an uniform electrical field. So for that, let us consider an uniform electrical field. Usually, uniform electrical field is given by parallel lines. Okay, by drawing parallel lines, we can state this diagram represents an uniform electrical field. Let us consider that uniform electrical field as E. Inside this uniform electrical field, I am placing a dipole having a charge minus Q at one end and plus Q at the other end, and it is separated by a small distance considered to be 2a. Already we have studied that when this dipole is placed inside an uniform electrical field, then this dipole will be experiencing a torque, and the torque experienced, you might have studied like this: tau vector is equal to P vector cross E vector, and if you are getting the magnitude or cross product, you can say the torque produced tau is equal to PE into sin theta. We have already studied about this. What will happen, or what this torque will do? This torque will try to rotate. This torque will try to rotate the dipole. Will try to rotate the dipole parallel to that of the field. Dipole parallel to the field. Okay, this is a small introduction. What will happen when an dipole is placed inside an uniform electrical field? About this we have already studied in our previous classes. Now, what we are going to study now? Now, for getting the potential energy, let us write a small description for this diagram. What is that description? You just consider, okay, you just consider an dipole, consider a dipole placed inside an uniform electric field, placed inside an uniform electric field, and let us consider that uniform electrical field as E. What will happen? That dipole, or we can write this dipole experiences a torque. Experiences a torque. That is what I have told in the previous condition. See, here I have told it experiences a torque, and the torque, the magnitude of the torque produced, tau is equal to P sin theta. And what will happen? And this torque will try to rotate the dipole. Rotate the dipole parallel to field. Will try to rotate the dipole parallel to what? Parallel to the field. This concept I have explained here itself. But while writing the question in examination, you just understood this concept, and you have to start right from this description after drawing the diagram. Now, what will happen? This torque produced will try to rotate this dipole parallel to that of this field. Now, what I am going to do? Now, I am going to rotate this dipole inside this electrical field against the torque produced through a small angle. For that, what I am writing, see, in order to rotate the dipole, I have to do a work. So, I am going to rotate the dipole So let us write like this. Rotate the dipole. Rotate the dipole from its initial position. Let us consider the initial position as theta dash to a final position theta. So if you want to rotate this dipole from its initial position to final position theta, we have to do a work. So let us write again. To rotate this dipole, to rotate the dipole from its initial position theta dash to the final position theta, a work has to be done. So if you want to do a work, then we are in need of an external torque, and that external torque should be equal in magnitude to that of the torque produced by the dipole inside the electrical field. So to rotate the dipole from theta dash to theta, a work has to be done. To do the work, an external torque is necessary. We are in need of an external torque. So let us consider that external torque is tau external. How should be this tau external? This tau external should be equal to what? This tau external should be equal to the torque produced on the dipole. So what will be the magnitude of this? Now we can say tau external or torque external. Let us consider like this. Modulus of torque external is equal to, we know torque external should be equal to the torque produced on the dipole. So the torque produced on the dipole is given by P vector cross E vector. If you are considering the magnitude of this torque, then we can say the modulus of P vector is P, the modulus of E vector is E into sine theta. So the torque produced, or we can say the torque that we are applying externally, torque produced externally or torque applied externally, tau external should be equal to the torque produced on what? The torque produced on the dipole by the electrical field, which is equal to what? Which is equal to P sin theta. Okay. Now what is the work done? Let us consider if the torque or if the dipole is rotated through a small angle d theta, then the work done is considered to be dW. In case of linear motion, we can say the work done is equal to force into displacement. Here rotation is cast, so it is angular motion. In case of angular motion, then we have to say instead of force, we have to consider torque. So torque tau external multiplied with or dot product of the angle through which it is rotated. Instead of dx or ds, we have to state d theta, angular displacement. Now we know that the initial position is theta dash and the final position is theta. Therefore, I can write the total work done W is equal to integral of dW. The integration should be within the limit, the initial position theta dash to the final position theta, which is equal to again integral of theta dash to theta. What is this tau external? Tau external is being given by the value P into sine theta multiplied with or dot product of this d theta. So that work done in rotating the dipole from the initial position theta dash to the final position theta is given as W, which is equal to integral of theta dash to theta of dW. That is equal to integral of theta dash to theta. Instead of tau external, I am writing P sin theta d theta. Now you integrate this equation and get the final answer. How to integrate or how to get the final answer? You see, therefore the torque produced or the work done W equal to, here P is the dipole moment, P is a constant, as well as the applied electrical field E is the constant which cannot be integrated. So we are taking P and E out. Sin theta d theta, when it is integrated, when sin theta is integrated, you will be able to get minus cos theta. And when you are applying the limit, the initial limit is theta dash, and the final limit we are calling it out as theta. So how I can write this? W is equal to, take this negative sign outside, minus of PE into, then I can write cos theta within the limit theta dash to theta. So how I can write this? Minus of PE into upper limit minus lower limit. Upper limit is cos theta minus the lower limit initial cos theta dash. Now how you can write this again? W, work done W is equal to, when you are multiplying this, you can say minus of PE into cos theta, then minus into minus, you will be able to get plus P into E into cos theta dash. So this is the work done on the dipole when it is rotated from the initial position theta dash to the final position theta. But still we can rearrange this. How we can able to rearrange this? The work done W is equal to, I can write like this, P cos theta dash minus P cos theta. So here the work done I can consider in rearranging the plus and minus. Then I can write the work done W is equal to P into cos theta dash minus P into cos theta. Or we can also write like this, W equal to PE, taking PE common, initial cos theta dash minus cos theta. See, what is this work done? This work done, okay, we can say this work done is equal to, this work done is equal to the difference in, work done is equal to the difference in potential energies, difference in potential energies between the two angular positions, between the angular positions, between the angular positions. What are the angular positions? That is theta and theta dash. That is final position minus initial position. So how you can write this difference in potential energy? Potential energy represented by epsilon. Difference in potential energy, you have to write it out as delta epsilon is equal to, difference in potential energy can be calculated by potential energy in the final position minus potential energy in the initial position. That we are calling it out as difference in the potential energy, delta epsilon. So how you can write this? Then when you are considering potential energy in the final position, potential energy in the final position is minus of P into cos theta plus, then what is this potential energy in initial position? That we can consider it out as P into cos theta. So we can say that the work done in moving the dipole from the initial position theta dash to the final position theta is giving you the difference in potential energy, and the difference in potential energy is represented as delta epsilon, which is equal to final potential energy minus initial potential energy, which is given by minus P cos theta plus P cos theta dash, not cos theta, this is cos theta dash. Now when you are, okay, this is cos theta dash. Now we can apply this in two cases. That is, by considering an initial position, we can calculate what is the final potential energy of the dipole, and when will be the potential energy is maximum and when will be the potential energy is minimum. So let us consider a special case. Okay, let us take it like this. What is that special case? You see, consider the initial position. Consider the initial angular position, or let us write the initial angular position as angular position. Initial angular position, we are considering it as theta dash. If the initial angular position theta dash is equal to 90 degree, that is the dipole is placed perpendicular to that of the electrical field lines, which is taken as reference, then initial potential energy U theta dash is equal to PE into cos theta dash. Instead of theta dash, you have to put it out as 90. Cos 90 becomes 0. So we can say initial potential energy is equal to 0. Therefore, if initial potential energy is 0, then the potential energy stored in the system of the dipole, kept in electrical field is given by, that is, from the initial position, if the dipole is rotated through an angle d theta so that it can reach its final position theta, then the potential energy of the system is equal to potential energy at the final position, which is equal to minus of PE into cos theta. So the potential energy of the system is equal to the final potential energy, which we can again writing it as a potential energy epsilon is equal to minus of P cos theta, or this can be written in vector format as minus of P vector dot E vector, because when you are taking the dot product between these two vectors, modulus of P vector is P, modulus of E vector is E, and since it is the dot product, we are adding the cosine value, that is cos theta. So the potential energy of the system is equal to final potential energy if initially that a dipole is placed perpendicular to that of electrical lines of force, or initial angular position is equal to 90 degree. So from this you can say this potential energy of the system epsilon depends, okay, it depends on theta also, depends on the final position theta also, in addition to what are in addition? In addition to the dipole moment P vector and the applied electrical field E vector. Okay, now when you are considering this potential energy of the system, when it is rotated through an angle theta from its initial position, when you can say the potential energy is maximum and when the potential energy is minimum. So let us put number 1 and let us write potential energy is maximum on the system, when the dipole, maximum on the system when the dipole is aligned, when the dipole is rotated or dipole is aligned anti-parallel to that of the electrical field, anti-parallel to the external field or to the electrical field, to the external electric field. What do you mean by this? That is, we have to rotate the dipole from its initial position through an angle of 180 degree or pi radians. So you have to rotate it through pi radians or you have to rotate it through 180 degree. Then we can say that potential energy of the system is maximum. How? We know the potential energy of the system given by epsilon is equal to minus of PE into cos theta, and if you are putting theta is equal to 180 degree or pi radian, cos theta will be equal to minus 1. Therefore, potential energy will be equal to PE. This amount of potential energy is considered to be the maximum value of the potential energy. Similarly, when the potential energy will be minimum, you again write point number 2. See the same concept. Potential energy is minimum. Okay, potential energy is minimum on the system. Potential energy is minimum on the system when the dipole is aligned. When the dipole is aligned parallel to that of, dipole is aligned parallel to the external electrical field. Parallel to that of the external electric field. Why you are saying that? If it is aligned parallel to that of the external electrical field, you see, if it is aligned parallel to that of the external electrical field means theta equal to 0. So, when it is aligned parallel means it is rotated throughout, it is rotated through 90 degree. From its vertical position to horizontal position, it has to be rotated. So, when it is aligned parallel, theta is equal to 0. If so, cos theta is equal to 1. So, what is the potential energy? Epsilon is equal to minus of PE into cos theta. Since cos theta is equal to 1, potential energy is equal to minus of PE. So, this value gives you the minimum potential energy, minimum value of potential energy when an electrical dipole placed inside an external electrical field. Clear? Now, let us recall or let us summarize what you have studied here. See, what is our concept here? We have derived an expression for the potential energy of the electrical dipole when this electrical dipole is placed inside an external electrical field. So, for that, what we have considered, in order to study about the electrostatic potential energy, in order to study about electrostatic potential energy of a dipole in an uniform electric field, you just consider an uniform electrical field E. See, here I have given a uniform electrical field E is given, represented by drawing parallel lines. Inside this, I have placed an electrical dipole having minus q at one end plus q at the other end, separated by a distance 2a. When a dipole is placed inside an electrical field, already we have studied that a torque will be developed or produced on that electrical dipole, and the torque produced is tau vector equal to p vector cross e vector. If you are getting the magnitude of this torque given by tau is equal to p sin theta. What this torque will do? This torque will try to rotate the dipole parallel to that of what? Parallel to that of the field. So, about this description of the diagram, I have written a small description in the below the diagram. That is, consider a dipole placed inside an uniform electrical field E. The dipole experiences torque tau, and the magnitude of the torque is p sin theta, and this torque will try to rotate the dipole parallel to the field. Now, what is our task? In order to determine or in order to get the potential energy of the system, we have to rotate the dipole. See, I have written here, we have to rotate the dipole from one position to another position. So, I am considering the initial angular position as theta dash, and the final angular position as what? Final angular position as theta. So, if you want to rotate it from one position to another position, we have to do a work. So for doing a work, we are in need of an external torque. That external torque applied on the dipole should be equal to that of the torque produced on it. So I am writing the magnitude of the external torque applied is equal to the torque produced on the dipole. The magnitude of the torque produced on the dipole is modulus of P vector cross E vector, which is given by P sin theta. So the torque external is given by the formula torque external tau external is equal to P sin theta. By applying this external torque, we can rotate the dipole through a small angle d theta. If you are rotating it through a small angle d theta, then the small work done, we are writing it as dw. We know work done is force into displacement in case of linear motion. In case of angular motion, the work done is the torque multiplied with the angular displacement. So tau external, that is the torque externally applied, which is equal to that of the torque produced on the dipole dot product of the angular displacement. Now in order to move it or rotate it from the initial position theta dash to theta, in order to get the final work done, let us integrate this above equation. You get integral of theta dash to theta dw, which is equal to integral of theta dash to theta P sin theta d theta. So on integrating this equation, P is a constant, E is a constant. When I am integrating sin theta, I am getting minus cos theta. And by applying the limit, final initial value theta dash to the final value theta, applying the limit, we get minus of P into cos theta minus cos theta dash. Now by rearranging, I can write this as W equal to the total work done is equal to minus PE cos theta, minus of minus will become plus PE cos theta. Say on rearranging, I can write this as the work done W equal to PE cos theta dash minus PE cos theta, or taking PE common, we can again write PE into cos theta dash minus cos theta. Now, what is this work done? This work done is equal to the difference in the potential energy between the angular positions theta and theta dash. The difference in potential energy is represented by epsilon. Difference in potential energy is delta epsilon, which is equal to epsilon theta. Epsilon of theta means this is the final potential energy minus initial potential energy. Difference in potential energy is generally defined as final potential energy minus initial potential energy. That final potential energy minus initial potential energy is here after getting the integration, that is minus PE cos theta plus PE cos theta dash. This equation represents the difference in potential energy. But what we are in need of what is the potential energy of the system after rotation. So let us consider it by taking a special case. What I am going to consider? Consider the initial angular position as theta dash, which is equal to 90 degree. That is, when you are taking or considering the dipole inside the uniform electrical field, it is placed perpendicular to that of the electrical field. Then only theta dash is equal to 90 degree. You take that position as the reference position. Then you can say when it is rotated, then u theta dash is equal to PE into cos 90, which is equal to 0. So initial potential energy becomes 0. So what will be the final energy? The final energy is the potential energy of the system, which is equal to epsilon is equal to epsilon of theta. Actually, epsilon of theta minus epsilon of theta dash, but epsilon of theta dash becomes 0. So final potential energy is equal to epsilon of theta, which is equal to minus of PE cos theta. This magnitude can be written in vector format as epsilon is equal to minus of P vector dot E vector. On taking the dot product, we can get it out as minus of P cos theta. So from this relation, we can able to say that potential energy epsilon depends on theta also in addition to P vector and E vector. So potential energy depends upon electrical dipole moment, electrical field, and also the angle through which the dipole is rotated. Now, when will this potential energy of the system is maximum and minimum? So, let us consider the first point when it is taken to be maximum. The potential energy is maximum on the system when the dipole is aligned anti-parallel. When the dipole is aligned anti-parallel means then theta is equal to the amount of rotation caused on the dipole should be equal to 180 degree. So if it is aligned anti-parallel, that is theta is equal to pi or 180 degree, then I can say cos 180 is equal to what? Cos theta is equal, cos 180 is equal to minus 1. So here instead of cos theta, if you are putting minus 1, potential energy is equal to PE. That is the maximum value. When potential energy is minimum, see, the potential energy is minimum when the dipole is aligned parallel to the external field. If it is aligned parallel to the external field, then theta becomes 0. Then cos theta is equal to 1. If cos theta is equal to 1, then we can say final potential energy is equal to minus PE. This potential energy epsilon is equal to minus PE gives you what? Gives you the minimum value of what? The minimum value of the potential energy. Okay, an important 3-mark question. Hope you should have understood. So compare this with the book reference. You take the book as the reference and try to work it out. By studying this, you can able to get an easier way of understanding. Thank you.